In this lecture, we will discuss about epitaxial growth. So, epitaxial structures are basically grown on integrated uh, circuits to improve the performance of the integrated circuit. And in what terms we are talking about the performance of the integrated circuit is, let us say that there is a junction. The junction can be NP, N plus P or NP plus. That means one is the junction which has the same doping concentration. The other is where the doping concentration of N is greater than P, and another is where the doping concentration of P is greater than N. So depending on the doping concentration, what are the so epi means upon and taxis means ordered. That means on the top of substrate. Okay, upon means on the top of substrate and taxis means ordered. That means of same crystal orientation as the substrate. That means epitaxial is means that arranged upon with the same crystal orientation as the base or the substrate orientation. So using epitaxy, a single crystal growth of the material is possible. Okay, and epitaxial process results in growth of very thin and controlled layer of around 0.5 to 20 microns. And what are the applications? You will see in power devices, which are discrete devices apart from integrated circuits. There is a requirement that if it is a p type, if it is n type material, we require intrinsic or a very low doping layer in between, and then over it a p-type material is desired. So this intrinsic layer is actually grown using epitaxial process. And MOS devices are also, the development of MOS devices also can be done using epitaxy, and also in bipolar devices to improve the performance of the devices in terms of low collector resistance and high collector emitter breakdown voltage. These can be achieved using epitaxial process. Okay. So epitaxial layer, as we have already discussed, has these advantages that it is possible to place a lightly doped region over a heavily doped region, which is not otherwise possible using diffusion or ion implantation technique. It provides a layer which is free from the material like oxygen and carbon. Okay. And apart from chemical vapor deposition, the other techniques that can be used for growth of silicon epitaxy are molecular beam epitaxy, liquid phase epitaxy, and solid phase regrowth. CVD is most commonly discussed in our subject. So what is the chemical vapor deposition? It is a chemical process to grow very thin layers of different materials, and it is particularly used, a technique used to grow silicon epitaxy. And we start with the substrate material over which this growth process happens. What are the steps? Silicon substrate is heated and to a certain particular temperature, and then it is exposed to a volatile gas which reacts and decomposes on a hot surface, and when it reacts it deposits a layer on a silicon surface. This is this layer has the same structure as that of the crystals, are oriented in the same structure as that of the base layer. So CVD is also used for the growth of silicon dioxide, silicon nitride, some metals such as tungsten, aluminium and copper, and yes, in semiconductors other than silicon such as gallium arsenide, polysilicon and so on. These are the CVD furnaces. You can see different reactors. You can actually draw one or two reactors in your exam. So some are vertical, some are horizontal, some are modified vertical, and so on. So you can actually draw some of them in your exam. Okay. In a CVD process steps, for visualization purpose, you can refer to this diagram that it has three main steps where it is a pre-clean, then deposition, and then evaluation. So the pre-clean is to remove particles and any contaminants from the surface of the wafer. During deposition, the wafers are loaded in a inert atmosphere, in a chamber where they are heated, and then chemical vapors are introduced, and then these vapors are removed. The deposition happens at the heated surface of the silicon. Thank you.